Okay, so there's two other ways that we can classify materials, and this is much more common than others. Going to consider, there's no pink material really, I'm not doing it by color, but the type of material, if you apply like a hammer, if you like drop it, actually you drop it like from your table, that's my table, all the way onto the ground, you just drop it and it just like sits there. Or it could be like, like the cliche Apple phone, where you just drop it and it kind of cracks. Shards everywhere. I mean, that's pathetic, but you know what I'm saying. So it shatters into different pieces. Yeah. God. Yeah. So yeah, normal. So you have materials that just don't break when dropped, and materials that break when dropped. So this is just an example of what you call a ductile. So ductile is like kind of softer material, and we have brittle, harder materials. Brittle doesn't exactly always mean harder. I mean, if you punch a brittle material, it generally would break, depending on how hard like the punching we're talking about. But a ductile material will be able to like take on the impact. So imagine like, I don't know, like a sponge and like a glass of like glass. Yeah. And what you notice about their stress strain diagrams in general of ductile and brittle materials, they look pretty distinct. So looking across. So for a ductile material, the stress strain diagram looks similar to the one that I described in the previous video, where it will come around, then kind of stop. Yeah. Whereas a brittle material would have, so instead of like a more slow slope, shallow slope, it has a pretty steep slope. And then it does that, and then like break. Yeah, it might not even like bend down. It might just stop here. Yeah. So this is like what a ductile material would generally look like. Brittle. Brittle is on the right. Yeah. So if you actually observe a ductile material breaking, what you would notice is that when it breaks, first it exhibits necking. Brittle materials don't really neck. Yeah. So brittle materials don't really undergo necking, they just break immediately. Like imagine like glass, only hot glass will start necking because it starts becoming ductile. But cold glass, it just snaps. So first when the thing breaks, what you notice of the two pieces is that you will see a piece of that neck. You'll see a little bit of the nose entering together. That's a thing that you notice. The other thing that you notice is that if I zoomed in on these, first, yeah, the nose parts. Yeah, those parts. The other thing that you notice is that you'll see like a dimple sort of shape, and you see a ball sort of shape at the other end. So this is generally what I think is because of the shock waves that happen when you pull it and it's a softer material. Whereas with brittle materials, they're quite hard. And so you'll see like a zigzaggy straight material. So it looks like a rough surface, like brick or something. Yeah. So if you like ever broke a brick and saw how that sort of looks sort of like that. Yeah. So it has kind of like a flatter shape. It's flat, rough surface. So that's the difference between like ductile and brittle fractures. Another thing I wanted to mention as well is the idea of toughness, which sounds almost exactly like hardness and strength and whatnot. But toughness. So toughness is the amount of energy needed to break, to fracture, or to deform. Yeah, to deform a material. the way that you interpret it in these strain diagrams is that, say, for a given strain amount, it's the area underneath the curve. That tells you, yeah. So you can think of it in a very crude sense. This is obviously not like precise, doesn't hold up to mathematical rigor. How stress is kind of analogous to force, because the only like conversion factor is the area. And then this is like the distance. But again, so strain is somewhat analogous to distance, where the conversion factor is the original length. Yeah. So remember how I didn't actually mention this earlier, but the work provided on the object is the force times the distance. So likewise, when you take like the stress times strain, what we're considering exactly here is the integral, or the area underneath the curve. Yeah. This is for the nerds out of you. But yeah. So the toughness of a material is the amount of energy required to break the material. The other way that you can think of this is impact resistance. So if you hit it with a hammer, or if you dropped it, or provided a sudden load, would it break or not? Or how much energy in that case would it require to break? Yep. At least if you're considering only yeah, I'll shift across as well. Up. Yeah. If you just considered just the elastic region, just consider that, and you're considering the area, the toughness just under the entire elastic region. So until the yield strain, stress strain. So yeah, if you just consider that, then you notice that this is a triangle. This is your yield stress. So like the more mathy kids out of you can write this as like the integral from 0 to EY of the stress, D strain. You can write it that way if you wanted to, but simply put, this is just this is a triangle, so you can just say half. So I can say that's equal to half times EY times strain y. Yeah, half base times height. So it's literally just that. And so this is only like for the entire elastic region. So this is like toughness over entire elastic region. Yeah. This number is given like a special name. That's why I'm talking about it. It's called the modulus, not elasticity, but modulus of resilience. Resilience. I can totally English. Resilience. Oh my god, I can't English. But you see what I'm saying. The modulus of resilience. Sorry. Yeah, the modulus of resilience is the amount of energy required to make something enter its plastic deformation. That's another way that you can interpret this. Yeah.